All right, for our final portion of lecture, we're going to deal with epoxides. Now, epoxides are a very specific ether, right? It is a cyclic ether, and it's a three-membered ring. This is known not only as an epoxide, but also as an oxirane. All of the cyclic ethers have a special name. For four-membered rings, oxetane, oxalane, oxane. But the only one that you need to know all about right now is the oxirane. And you do need to know the term oxirane and epoxide, because they're both useful, especially when you are naming. Now, for nomenclature, much like with ethers, there's two different ways to name an epoxide, except it's not common in IUPAC. Both of these are useful for naming. And so, okay. So one is more simple and one it treats it as a substituent. So we're going to go with the oxirane parent scheme, right? So this is the name. If you have a fairly simple structure here, and we're going to, it's this portion down here. So you can have these different R groups, and so I'll do something like this. Why not? And if I'm going to use the oxirane parent scheme, then the oxirane is the parent, and it will be numbered always with a 1 on the oxygen, and then 2 and 3, it depends on locant. Since numbering counterclockwise would give me a 2, and a 3 substituent, that's what I'm going to do. 2, 2, 3 is preferable to 2, 3, 3. Then you're going to just arrange alphabetically. I would have a 3-bromo, 2, 2-dimethyl, oxirane. You see that in their example as well. There are 2 ethyl groups, 2 methyl groups. I'm guessing priority was given to the ethyl groups because of the alphabet. So it's 2, 2-diethyl, 3, 3-dimethyl, oxirane. Now you can probably see this is only really useful if these R groups, or like where the bromine is, are fairly simple and easy to name. And so if you have something more complex, or if you just prefer this method, you can also use the epoxy method of naming, and it treats the epoxide as a substituent on a parent. So this makes it a little bit easier if you have a more complex parent, or more complexity to your molecule. So what you would do if you have something like this, and let's up it a little bit. We could even have a double bond in there. What else could we, that seems good enough. So we would number, because the double bond would affect the parent, we would number to give the lowest numbering possible to the parent. 6, 7. This would be a heptene, right? A 2-heptene, and our epoxide would actually get 2 locants. So even though our double bonds and triple bonds only get 1, right? We only say the first carbon in the double bond. For the epoxy group, you list both carbons that are involved. So this would be 4,5 epoxy 2-heptene. Now to get right to the nitpicky, nitty-gritty details, it also is a unique substituent because, one, you number both carbons, but also it always goes right before the parent. So it does not tend to kind of abide by alphabetical rules. It's not something that I am strict about or would take off for, but especially if you're working on a practice problem on a computer, it's good to know. So you see in this example here, we've got 1, 2, 3, 4, 5. We're going to number from right to left to give the lowest numbering possible for all of the various substituents. We've got a 3-ethyl group, a 2-methyl, and then a 2,3 epoxy. Everything goes in alphabetical order except for the epoxy, and it goes right before the parent. Again, it's a little bit of a random nitpicky detail, but that is the rules for naming epoxides. So as always, make sure you do some nomenclature practice. For preparing epoxides, this is actually a reaction you already know. We just didn't take it apart. So when you take a alkene and you use a peroxy acid followed by H3O+, you actually already did this reaction, right? You know it makes a alcohol. The first step is actually making an epoxide. So if we just look at our CO3H, that is going to give us an epoxide intermediate. Now they could be wedged or dashed, they just have to match. Right? And so that is one way to make an epoxide. Now something that you have to be aware of. Yes, you can absolutely write peroxy acid. You can write RCO3H. But you've got to know MCPBA as well. That is a specific peroxy acid. It is very, very common. MCPBA, I'm not going to ask you to draw the structure, but you have to know that acronym. Because it's so common, it's going to be in various practice problems. You might see it on the test. Right? It is an important peroxy acid reagent. You don't have to know the mechanism behind it, but you do need to know that it will make an epoxide. It is stereospecific, but all I really care about is if it's on a ring that you show 2 wedges or 2 dashes. The other way you can prepare is it's really just Williamson ether synthesis, but cyclic, right? So if you have a halohydrin, and halohydrins, you guys know how to, hydrin, you guys know how to make these from chapter 8, right? You have an OH on one side, you have a bromine on the other, or chlorine, or even iodine. If you take this and you treat with a pretty, in this case, sodium hydroxide should work. If you treat with a strong base, it's going to deprotonate the alcohol, and then it will attack your alkyl halide, which is just next door. And then the bromine will leave. So it's actually just Williamson ether synthesis, but intramolecular. And I didn't have a ring, so let's not introduce one. And that will also lead you to an epoxide. This mechanism is exactly what we did before. Deprotonation, SN to attack. We have a ring at the end. So you have 2 ways to go from a double bond to an epoxide. You can use MCPBA, peroxy acid, or you can make a halohydrin and then treat it with a base. As far as enantio's selective epoxidation goes, you can skip this whole section. I am not going to ask you about section 9. Now, the important reactions of epoxides. Ring opening. There's a lot of different reactions that you can use, and we want to pay special attention to the regiochemistry. We can react with hydroxides, alcohols, alkoxides, hydride reagents, and Grignards, and we're going to look at all of those, but it's really just one mechanism. So when we take, and this is technically basic conditions, right? It's going to either be a very strong nucleophile or a strong base. It will not be acidic. It is what we're going to say here. Now, what we're going to do is we're going to take an epoxide, and here they're specifically using hydroxide, but we're going to use a generic nucleophile. This nucleophile is going to react with an epoxide because the epoxide is under a lot of strain, torsional and angle strain. Because this is not an acidic environment, making an O- is okay. So OR isn't usually a very good leaving group, but in these conditions, it's okay. So you'll form a new bond to the nucleophile, and then you will have O-. And in most of these steps, you're going to add water or acid at the very end, or even an alcohol. And it's because you just want to protonate and make whatever this is, nucleophile, adjacent to the carbon with the alcohol that you're going to make. Now, you can see here how hydroxide works, and we wind up making a diol. Just a little bit of thermodynamic conversation. But this works. This nucleophile could be an OR group. It could be sodium cyanide, so it could be a cyano group. It could be a thiol. It could even be a Grignard. You could put an R group here. We usually show the Grignard working with the carbonyl, but the epoxide is also reactive. It works very similarly there. You could even use LAH. Now, you definitely don't need to know the mechanism on that one, but it's the same idea. It's going to add H's across the, is going to add an H to your carbon, and it will, then the H2O will provide the H for the alcohol. You should be able to predict using any of these reagents. They're all going to react in basically the same way. Now, what about regiochemistry? Everything on this chart, if we had an asymmetric oxirane or epoxide, and we treated with any of these reagents, so we'll use sodium cyanide, why not? 2, work it up with H2O to protonate that alcohol. It is going to add to the less hindered side. Right? It's just a steric preference. So we would add in our cyanide, and then we would wind up with OH. Now, again, this could be an OH, it could be an OR, it could be an SH, an R, or an H, just depending on what reagent set you choose. It will go to the less hindered side. So see, you can see here another example just using a generic nucleophile. In this cyclic structure, you can also bring in stereo configuration. It is still, it's an SN2 reaction. So the nucleophile is adding from the opposite side of the ring from the leaving group. So your nucleophile in this case wound up wedged, and the OH wounds up, nucleophile is dashed, alcohol is wedged. So the OH is always on the opposite side of the ring from whatever you added. Now, under acidic conditions, it's a little bit tougher in terms of regiochemistry. First, let's look at our mechanism. So we're really going to have two sets of acidic conditions. All right, so you're either going to be dealing with HX, or you're going to be dealing with water, or you're going to be in acid, or an alcohol in acid. All right, so let's just go through these real quick. HX, you're going to wind up with an alcohol on one side, X on the other. If it's water, you're going to wind up with a diol, right? That's the second half of the reaction that you already knew. If you use alcohol instead of water, you're going to wind up with an ether and an alcohol. Now, these all start with the same basic mechanistic step, and we see that right here. You're going to protonate, right? You've got acid present in all three of these, and you are going to go ahead and make that into an even better leaving group. It's going to make these positions more nucleophilic, or not nucleophilic, more electrophilic. So something like an X or a water molecule or an alcohol can attack, and the OH can leave. This has to happen first. You're not going to make O- if you're in an acidic environment. All right, now when you add X, it's pretty easy. There we go. and you are done. However, when it's water, you do have an extra step, right? So you can use water or alcohol, and they both are going to require an extra step. And that's going to be dealing with that proton at the end. So you have an example of water, so I'm going to use an example of an alcohol next to it so you can see both. The first step, we're going to protonate. The second step, the alcohol is attacking. The plus charge is on the oxygen. And we're going to open it up. And then that gives us the alcohol. The alcohol that added, right, still has its proton. And so you do have to have one final step to get rid of it. Now, we're not in a strong base, so you don't want to use a strong base. So all that you really know that you have is alcohol. And the alcohol can help you here. It can deprotonate. And then that leaves you with your final product. Now, what about regiochemistry? This one's a little bit different. It's usually to the less hindered side. So, for instance, primary versus secondary, the X added to the primary side. Unless there is a tertiary position. Then the nucleophile will go to the tertiary position. So for instance, in this bottom example, you have primary versus tertiary. The X will go here to the more substituted side. Now, why is that? It has to do with the energy of the transition state. As the bond is starting to break between the O and the C, you do get a partial positive. And what stabilizes a positive charge? More R groups. Think about your carbocation. What's the most stable carbocation? The tertiary one. So this brings down, this stabilizing feature right here brings down the energy of that complex so much that we wind up seeing this being favored, the attack here being favored. If it's primary and secondary, the energy difference isn't big enough, and so sterics win. But with tertiary, thermodynamics win. So when you are predicting products, you need to decide, what are these carbons doing, right? This one here is secondary. This carbon is attached to a CH2 and a C. This carbon here in green is tertiary. It's attached to a CH2, a CH, and a CH3. So the OR group from the alcohol is going to attach to the more substituted side. So the OH, right, when the alcohol attacks, the OH is going to leave. It keeps the same stereochemistry, so it's still wedged. The OR is coming from behind, so it pushes the methyl group forward. And that's it. You need to practice these. You're absolutely going to see questions about epoxides and ring openings on the final. But we are so close to being done. We're just going to do a little bit of naming here for thiols and sulfides. Thiols are the sulfur derivative of the alcohol, and they're pretty easy to name. If they're the only functional group you have, you are going to drop nothing, right? So you're looking for the longest continuous chain with the thiol, and then you're just going to add the word thiol onto the end. So this becomes ethane thiol. That's not an H. Thiol. There we go. Here, if it was an OH, it would be based on butanol. But when it's an SH, you still have butane and then thiol. You do have to put a number where the thiol is, so you do see the 1 there. Let's see. If it was an alkene, we could deal with that as well. This would be a 1, 2. This would be a 1. Actually, let's call it a but. No, How about it's nothing about butane there. This is a cyclobute 1-ene 2-thiol. And you would probably put an extra E in there. There we go. It's about as complicated as we're going to get with that. If the SH is not going to give you the parent, so if the SH is a substituent, you are going to use the term mercapto, right? So, for instance, OHs are higher in priority, right? They will give the parent name if you have them there compared to the thiol. So, if this is a butanol, then we need to be able to name this as a substituent. And so that's where the 3-mercapto, 3-methyl-1-butanol comes in, still listed in alphabetical order. You would also use di, tri, tetra if you had multiple thiols. So you've got a dimercapto compound here. Thiols don't smell good. They very much not a pleasant smell. Skunks have thiols in their spray. Methane thiol is what you're actually smelling when you're smelling gas. It's added to methane and propane and butane so that you know if you have a gas leak, because those natural gases don't typically have their own smell. It is a strong nucleophile, so we usually see it with SN2 reactions over E2. Right. The reactions that they go through at first are ones you already know, so it's a good review there, but we are not going to do any new reactions. It's worthwhile noting that this is a disulfide, but I am not going to quiz you over that. Those are really interesting bonds in quaternary structures when you get into like biochem. They're important bonds in the 3D structure of curly hair. It's a fun little bond, but we're not going to do much with them. The last thing I want to cover is just sulfides. Naming sulfides. Nomenclature. Oh, there we go. It's just as easy as naming ethers. There's a common way, and then there's an IUPAC way. The common name, it follows the same pattern as the ether. It's alkyl, alkyl, sulfide. So if it is symmetric, it could be something like diethyl sulfide. Let's say we have something a little bit more interesting. Let's say 1, 2, 3, 4, 5. This would be a cyclopentyl propyl sulfide, right? Pretty straightforward. You just have to remember the word sulfide. Sulfide as a substituent is more common in more complex molecules, because like ethers, it's not very high up. Oh, I'm really testing myself with spelling today. If it's not part of the parent name, it is a methyl thio, right? So mercapto is for SH, methyl thio is for SR. So you can see in this example here, if this is named 1, 2, 3, 4, because the locants, you'd have a 114 is better than a 144. You have the dichloro and then 4-methyl thio. Now it's in parentheses, so it's not ambiguous about that methyl group. I'm not real picky about it, but that's why they're there. You just treat it like any other substituent: fluoro, chloro, methyl thio. All right, so as always, can't recommend enough that you practice naming. You are not going to need to know any of the reactions of the thiols and the sulfides, so you can skip the rest of 11. 12, I would absolutely recommend that you read. You're going to be doing synthesis problems. Your extra credit involves it. Your final will have synthesis problems that involve epoxides. And so reading Klein's strategies is always a great idea. You can see here different ideas for if you want to add an OH and something else to adjacent carbons. Using an epoxide is a great idea. using it as a way to enhance your carbon skeleton is really kind of a neat way to use it in this Grignard reaction. All right, we're making a Grignard out of an alkyl halide. Very, very easy. Then the Grignard can attack the epoxide. Open it up, and it's a way to add 2 carbons and an OH. Now, you could do this in another way, still using Grignards and get the alcohol here. With synthesis, you have a lot of options. Hopefully, you're recognizing that with more options comes more need for practice. And again, I'll let you read that one on your own. Please work on your synthesis. Please come see me and ask questions. Email me. I'm still here for you. If you've made it this far, I'm super proud of you, and I really appreciate you working through all of these with me. And I will see you in the exams.